Hi everyone, I'm Natalia Porqueres. I'm a postdoc at Imperial College and I'm also a member of the Aquila Consortium. So thank you for tuning into my talk. Today I will talk about Bayesian hierarchical models of cosmic shear and how we can use these methods to constrain the cosmology and the matter distribution. So first of all, the first question is, why do we want to use Bayesian hierarchical models? Well, we know that these methods can provide more accurate and more precise results than the standard analysis with summary statistics. The idea behind Bayesian hierarchical models is to build a full data model for the quantities that we measure. And in principle, with these methods, you can use every data point and you are not restricted to a set of summary statistics that cannot capture all the information in the data. Also, the Bayesian hierarchical models are a way to avoid all the problems connected to the summary statistics. So typically, when one uses summary statistics, like the correlation functions or the pseudo-CLs, one assumes a Gaussian likelihood. And then the question is, what is the covariance matrix? But it is very difficult to get an accurate estimate of this covariance matrix, and this might bias your results. So one way to avoid this problem is to use Bayesian hierarchical models that bypass the summary statistics and directly compare the theory and the data at the field level. So these kind of methods, the Bayesian hierarchical models, are a field-based approach, and they consist of simulating some fields that then we can compare to the data at the pixel level. And by doing this, these methods correctly deal with the non-Gaussianity of the field, and they can extract information from the high-order statistics. So all this leads to more accurate and more precise results. And this was also shown here in this recent work by Florent Leclerc and Alan Evans. So here they tried to constrain two parameters from log normal fields, and these parameters control the non-Gaussianity of the field. So the green contour are the posterior distribution that they obtain when they base their analysis in the two-point correlation function, assuming a Gaussian likelihood. And you can see that these posterior contours are biased. So this means that the two-point correlation function can sometimes give inaccurate results. Then they also do the analysis with a two-point correlation function, but in this case, it's a likelihood-free inference. So it's based on simulations, and this is the blue contour. And this blue contour is centered at the correct values. So the likelihood-free inference in this case is giving accurate results, but it's still imprecise because it has large error bars. And then finally, there is the orange contour, which is a field-based approach using a Bayesian hierarchical model. And in this case, the results are accurate and much more precise. The error bars are much tighter. And this shows that using Bayesian hierarchical models can give tighter error bars and more precise results. So that's a bit the motivation why we want to build a Bayesian hierarchical model for the analysis of weak lensing data. But for that, the first thing we need to decide is what physics we are going to include in our analysis. So in this method, what we are going to do is to start with some cosmology. At the end, what we want to constrain are the cosmological parameters. So we have some cosmology, and then we simulate some shear fields, and we compare the result of the simulation to the data at the field level. But the first question is what kind of physics we model into and we put into this simulation. So one option would be, for example, to directly sample the shear field from a Gaussian prior. That's an option you can find in the literature. And another option is also to start sampling from the density field instead and use a log normal prior. So these options are very well justified from the point of view of information theory if you only know the mean and the standard deviation of these fields, if you only know the first and second order statistics of these fields. But we actually know more about the physics of the large scale structure. We know how the matter fluctuations evolve under gravitational instabilities, and we know how the cosmic structures form and evolve. So if we use Gaussian and log-normal priors for these fields, we are not taking advantage of all this additional information that we have from the large-scale structure. So that was a bit the motivation for us to build a Bayesian hierarchical model in which we include a model of the nonlinear gravitational clustering and the cosmic structure growth. So in our model, we start sampling, or the quantities that we sample are the initial conditions that we know they are very well described by Gaussian statistics. And then the ingredients that we put in this simulation are basically a Gaussian prior for the initial conditions, and then a gravity model that evolves the initial conditions to the redshift that we want to analyze. And to do this, we use the Borg framework. So in more detail, our Bayesian hierarchical model looks like this. So we sample the cosmological parameters from uniform priors. We have a uniform prior for each one of the parameters. And then we use this cosmology to define the Gaussian prior for the initial conditions. So the cosmology here determines the power spectrum of the initial conditions. Then we draw random realizations of initial conditions from the prior, and we evolve this in time using the gravity model. And the gravity model also accounts for light cone effects because we want to analyze data at high redshift, so we need to take all these effects into account. So in Borg, we have several gravity models, and it is straightforward to switch from one to the other. So the more relevant for this work are Lagrangian perturbation theory and particle mesh simulations. So at the moment, we are using Lagrangian perturbation theory because we are still testing and developing the method. But in the future, when we apply this to real data, we will switch to particle mesh simulations to get a more accurate density field at the small scales. And it's of course more expensive to run particle mesh simulations, but it is still doable. So with all this process, we obtain some density field in 3 dimensions. And now we can integrate this density field along the lines of sight, taking into account all the lensing kernels. And with this, we obtain the shear fields, and we are doing this now in the flat sky approximation. So we obtain different shear fields, one shear field for each tomographic bin that are indicated here with the label B. And the redshift distribution of sources for each tomographic bin is part of the input to the method at the moment. So with this, we have now some shear fields that we can compare to the data using the likelihood. And to write down the likelihood, we assume that the noise in the data is Gaussian. So we have a Gaussian likelihood that runs over the different tomographic bins and the different pixels on the sky. So we do the comparison of these fields pixel by pixel. So in this method, the dependence on the cosmology is threefold. So the method depends, or this model depends on the cosmology through the geometry, the growth of the cosmic structures and the gravity model, and the initial matter power spectrum. So these are the things that allow us to sample and constrain the cosmological parameters. So we have implemented this in a statistical framework that basically has 2 blocks, one that samples the density field, and this gives us a sample of the initial conditions that then we can use to sample the cosmology. And in this case, the cosmological parameters that we are sampling are S8, H, and omega m, because these are the ones that we expect, or that we can expect to constrain with lensing data. And then we iterate this in a Monte Carlo Markov chain framework. And this is a very high dimensional problem. So we are sampling the density field in every voxel. And this means that in a normal analysis, we are dealing with millions of parameters. So to test this method, we use simulated data. So we did a simulation that covers 1 square gigaparsec across the sky and 4 gigaparsecs in the radial direction. And we have lower resolution in the radial direction because the lensing is not very informative in the line of sight direction. So then we added Gaussian noise to the data, to the simulation to generate the data. And this noise has a variance that corresponds to 30 sources per square arc minute distributed equally between the 4 tomographic bins. And this is these 30 sources per square arc minute is also what is expected for Euclid. Then we also added a mask with 2 components, one for unobserved regions and one for bright stars. And for this kind of methods, it's very easy to deal with masks. So if you have a mask pixel, you give this pixel an infinite variance. So this is another of the advantages of this kind of methods, that they can deal with complicated masks that might be challenging for other methods based, for example, on the power spectrum. So we have applied the method to this simulated data. Here are some of the results. So here you see the posterior distributions for omega m, h, and sigma 8. And in red, we indicate the value of the true parameters, the ones we use to generate the mock data. So we have uniform priors for each one of these parameters. Well, in this case, we are actually sampling S8 instead of sigma 8 because we get shorter correlation length sampling S8, and the sampling is more efficient, but we can then transform this to sigma 8. And then, yeah, so we have uniform priors for these parameters, and you can see that in the case of H, the posterior distribution is just basically the prior because the lensing is not constraining for this parameter. But in the case of omega m and sigma 8, we are recovering the correct value. So the mean of the distribution agrees with the true value. So these are the results for the cosmology, but we are also sampling the density field. So we can look here at some density fields. So here are the initial conditions and the final densities for one tomographic beam. So what we have done here is to project the density fields on the sky, considering the lensing weights that correspond to the tomographic beam. So yeah, so the first column here is the true fields, the ones from the simulation to generate the data. And then the second and the third column are the mean and the standard deviation of these fields. And we have estimated this or computed this from the posterior samples. So we can compare the first 2 columns, and you see that we are recovering the correct structures from the true fields. If you look at the standard deviation, you see that we have these areas with higher uncertainty, and this corresponds to the mask regions. So in the mask regions, we don't have direct information about the density field because we don't have data, but the method can still provide some information about what densities are physically possible in these areas. So, so here, this is basically a visual comparison of the fields projected on the sky because the lensing is not informative along the line of sight. But we can, of course, also look at the clustering properties of these fields. So we can look at the power spectrum of the initial conditions. And in this case, we are measuring the power spectrum in the box, so in the 3-dimensional initial conditions. So here, the dashed line is the truth, the one from the simulation, and the green lines are measured in different posterior samples. And you can see that the posterior samples have the correct power spectrum of the initial conditions, which is, of course, depending on the cosmology, on the value of the cosmological parameters. So yeah, so at this point, another question that we can ask ourselves is whether these densities can explain the data. So for that, we did a posterior predictive test. So what we do is we take several samples of the initial conditions with the corresponding cosmology for each one of these samples and run the forward model on these initial conditions and see whether we can recover the shear fields that we input as data. So here you see the simulation, then the data with the noise and the mask effects, and below the mean and the uncertainty of the posterior predictive test. So in the uncertainty, you see again the effect of the mask. Maybe here it's easier to compare directly with the data. And we can also compare here the mean and the truth. We can also compute the residuals between these two fields. And this is shown here. So the histogram shows the residuals for the real and the complex component of the shear field for one tomographic beam. And you can see that this histogram is narrower than the noise distribution, which indicates that the method or the inferred quantities can explain the data at a subnoise level. So summarizing, it is possible to do Bayesian analysis of weak lensing, including nonlinear gravity models. And doing this kind of Bayesian hierarchical models, we can bypass the summary statistics and extract more information from the data that we could not access if we use correlation functions or power spectra. And we can use this kind of methods to jointly constrain the cosmology and the matter distribution. And the next thing we are going to do with this method is to do a comparison with the constraints for cosmology we would obtain using summary statistics, for example, but in this case for the weak lensing, but directly for the weak lensing. So this is the end of my talk. So thank you very much for listening, and I'm looking forward to the discussion. So see you soon.